Yeah, I would like to tell you a little bit about my paper that came out actually last week. It is titled The Evolving Three-Dimensional Landscape of Human Adaptation, and you can scan the QR code if you want to read it. So for this research, but also my previous research, I've been looking at hominin evolution over the past 2.5 million years. And as you can see in the lower right corner, there's a hypothetical, like very simplified phylogenetic tree of the genus Homo with several of the species associated with this genus. On the left side, you see a map with stars. These stars represent archaeological and anthropological findings that were assembled by Pascal Raya and his team. I think I kind of came into this project at a very good time because we had this amazing data set for 2.5 million years. And so much work went first, of course, into finding and excavating and then assembling the data set. And at the same time, in our institute, we had a 3 million year climate run. So this led me to think like, okay, how is the climate and like evolution related? Like everybody here, but I had access to 2 of these data sets to do that. And as most of us look at climate factors like temperature and precipitation, vegetation, and hydrology, we think about adaptation and migration, which are then associated with things like cultural innovation. And in the session this morning, we saw that many people actually try to model with agent-based models or dispersal models, model combinations of all of these different aspects of human evolution. For my research specifically, I wanted to focus on vegetation, and I really like statistics. So instead of explicitly modeling, I used data analysis and statistics to extract the climate and vegetation at specific locations of hominin findings. To do this, I used the data set from Pascal Raya, which has entries that have a species associated with them. They're found at a certain location, so they have a latitude and longitude, and then they have an age estimate, a minimum and a maximum age. And then I combined this with a climate data set that was run in our institute by Dr. Kyung-Suk Yoon. This climate model is forced using orbital parameters and greenhouse gases like CO2. And because I was specifically interested in vegetation, I used the CO2 and the output variables temperature, precipitation, and clouds to force an offline vegetation model called Biome 4. From this biome model, we get 28 different biomes, which I looked at, but I also tried to look at the biome diversity. So to translate these biomes into biome diversity, I looked at the biome at a specific grid point and then the 8 surrounding grid points, and I counted how many different biomes are within this within these 9 grid points. So if you have a border between tropical forest and grassland, the border of these 2 environments will be 2, but in the middle of the environments, the biome diversity will be 1. And the idea is that there is more food diversity in your in the neighborhood for early humans to use. Sorry. Okay, so then when we have a map of this, we can do this analysis all throughout our 3 million years. And we can have, dots will appear on this map in a little bit with where hominins were found. These will be red dots, and they will mostly be located in areas of high biome diversity. And they should appear. Ah, there, we have the first one. You can see that the dot is, well, still only one, but yeah, the dots are starting to appear, and they are mostly in places with high biome diversity. The other thing you see is that the locations of high biome diversity remain pretty stable through time. Initially I tested if hominins actually appear in places of high biome diversity. To do this, if you make a distribution of all the land points within Africa and Eurasia, and you make another distribution of only the hominin sites, you see a shift between the two distributions in that the land points have a very low biome diversity, and the hominin site locations have are clustered in higher biome diversity areas. So from this and more statistical analysis, we concluded that hominins prefer biome diversity, and this was the conclusion of my first paper. Now that we know, so you're just going to have to believe me and trust me on this one, but we can discuss this further. Now that we know that early hominins liked high biome diversity, we were wondering what are the environmental drivers to that lead to high biome diversity. We wanted to look at climate factors, but in addition to this, we also wanted to look at geographic factors, because when you see all of the hominin locations that we use in our database and you put them on a relief map, you see that most of the locations are either around mountains or rough areas. So when you have a sloped environment, we know that the temperature and precipitation change much more rapidly than if you just have a very flat environment. And therefore the biomes could hypothetically change faster, which increases the spatial biome diversity. So to test this, we used the eTopo dataset at a 30 arcsecond resolution, and then we calculated the slope of this dataset, which we call the roughness, and we integrated this on a 0.5 degree grid, so we can compare it to our biome dataset. And when you overlay the roughness data with the biome diversity, you can already see that the areas that light up in biome diversity also have high roughness. So specifically around the Himalayas, the mountain areas, the Alps in Europe, and the East African Rift Valley. So then when we make a joint distribution of biome diversity and roughness for hominin locations in red and all of the land points in Africa and Eurasia in blue, we see that that biome diversity and roughness scale with each other. So when we have a higher roughness, we also have a higher biome diversity. In addition, there is an offset between the line between the land points and the hominin locations. So for whatever roughness we see, the biome diversity is higher for hominins than if you would consider all land points. This again points towards this preference for higher biome diversity. This is a relatively simple view, only between biome diversity and roughness. We wanted to look also at climatic variables, in particular temperature and precipitation, and then we wanted to see if there's any nonlinearity. So to do this, we used ACE analysis. ACE is a non-parametric regression analysis, and it translates your variables, or it transforms your variables to a distribution we call phi. All of the phi's of all of the different variables sum up, for all of the different predictor variables, they sum up to your target variable. Yeah, so we can use if higher roughness or higher temperature, we can then translate this to biome diversity. In addition, the range of phi can be seen as a measurement of the overall contribution of each of the predictor variables. So then when we look at this, we see for roughness on the top, we're first going to look at all of the land points within Africa and Eurasia again. We see that for roughness, it has a very linear relationship with biome diversity, and that this is the case for all of the different roughness. So even in very flat area, it keeps having a mostly linear relationship. Well, if we look at temperature and precipitation, we see that there are climate optimums. For temperature and precipitation, this makes sense, because if we look at the biomes, they are mostly controlled by temperature and precipitation. So in the kind of middle range of like temperature and in the middle range of precipitation, you have a lot of different biomes that are possible. So the shift from one biome to another biome will also be more easy or faster. And therefore the chance of having a higher biome diversity is there. So we see this in temperature and precipitation, but not in roughness. In addition, you can see that in the temperature and precipitation extremes, if we color the biomes by the different groups, we see that there is an ordering. Again, this makes sense because in the extremes, we see that there's only a chance of one type of biome. But it's interesting, there's no such preference in an area of the roughness for our data. So then when we look at only the hominin locations, we see that the roughness still scales with biome diversity, and that there is a temperature and precipitation optimum also of within the hominin niche. Then when we look at the contribution of each of these variables towards biome diversity, we can see that roughness is actually more important than either of the climatic variables, which is something that we did not expect. So that view was for like all of the hominin sites all through time. Now, if we want to understand the evolution of this hominin niche, and then specifically for roughness, but we also want to look a little bit again at biome diversity, temperature, and precipitation. We grouped early African hominins together. So these are all of the sites that are associated with habilis or agaster. We grouped Heidelbergensis and Neanderthalensis together in the middle, and then Homo sapiens in the bottom. So this kind of represents migration and adaptation over time. We see that the roughness niche increases, that there is an increasing roughness, so there's an adaptation towards more rougher environments. In addition, there is a shift towards higher biome diversity, even though initially the early African hominins already liked higher biome diversity, but we see adaptation towards more extreme biome diversity. Then for temperature, we see a a shift in the hominin niche towards lower temperature, and this makes sense because Europe, so the bottom two are where the bottom two hominin groups are found. They were found in Europe, and Europe is colder than Africa. In addition, we see for precipitation that there's a shift towards towards drier and wetter environments. More specifically, looking at area roughness, but now we're looking at a rolling average over time of groups of 15 hominins. We see that there are actually two different time periods of expansion towards a higher area roughness, which is with a small decline during the mid-Pleistocene transition. So the mid-Pleistocene transition also has been associated with human bottlenecks and depopulation in Europe, and other things like mammal extinction. So this is a interesting time period for further research. So to conclude, we see that biodiversity measures scales with topographic roughness, and that this is an important predictor for a more important predictor for diversity than temperature or precipitation. Human species were located in areas with rough terrain, which in part is because of the increased food diversity. And over the past 3 million years, early humans adapted towards rougher terrain, colder, drier, and wetter climates. And that this adaptation towards rougher landscapes was gradual and possibly interrupted during the mid-Pleistocene transition. That's it.